For a given electric circuit, Norton's theorem suggests an equivalent circuit called the Norton's equivalent circuit, just like the Thevenin's equivalent circuit. How different is the Norton's equivalent circuit from the Thevenin's equivalent circuit? Let us discuss this. So let me consider a circuit network, and let me say that this is the Thevenin's equivalent of that circuit network across A and B. So this is the Thevenin's equivalent circuit. So this has an equivalent impedance Z Thevenin for AC and an equivalent voltage source having a value V Thevenin, the direction as indicated. Now for this circuit network represented by this Thevenin equivalent, let us say we will develop another equivalent called the Norton's equivalent, which is actually a dual of this Thevenin's equivalent. Let us see how this looks like. So this Norton's equivalent also has these two external nodes or the output nodes A, B, and to these nodes is connected an impedance as seen from the nodes A, B, and this we will call as the Norton impedance Z Nor. And instead of a voltage source, as you see in the case of the Thevenin equivalent, here it will be a current source. So let us put a current source here and call this as I Nor or I Norton, the direction of the current as indicated by this arrow. So you see that these two are actually duals. You have a voltage source and a series impedance. You have a current source and a parallel impedance. However, note that these two impedances are the same because whatever be the equivalent, whether it be Thevenin equivalent, Norton equivalent, or some other equivalent, or even the original circuit, the impedance seen from this terminals A, B inside into the network has to be the same as what you would see even from the Norton's equivalent terminal A, B. So what do you see from the Thevenin's equivalent terminal, equivalent circuit terminal? You would see that the impedance of this circuit network, the impedance, what do you encounter? You encounter ZTH or the Thevenin impedance. The impedance of VTH is 0, impedance of a voltage source is 0. So therefore from A to B you have an impedance of ZTH only. Likewise, in the case of the Norton circuit, if you move from A to B, the impedance that you see across A and B is Z Nor. The impedance of the current source is very large, infinite in the ideal case, and therefore this doesn't come into the picture. So what you see across the terminal is Z Nor. Now as the impedance seen from the terminal A, B, whichever be the equivalent, has to be the same because it is the same physical circuit, you can come to the conclusion that Z Nor is same as Z Thevenin. So finding Z Nor for the Norton's equivalent circuit is same as finding the equivalent impedance of the circuit through the Thevenin as of the Thevenin equivalent circuit. Consider this Thevenin's equivalent. What is V Thevenin? V Thevenin is nothing but the voltage across VAB when AB is open circuited. So that is V Thevenin, which is VAB at open circuit across AB. So what is the equivalent notion for the Norton's equivalent? In the case of the Norton's equivalent, we short circuit A and B. So A and B is short circuited. Under that conditions, what is the current that flows from A to B? Let us say we call it as IAB. Then this Norton current I Nor equals IAB when AB is short circuited. What is this value? You can take the same Thevenin's equivalent, because it is the same circuit. Let us short A and B. What is the current flowing through this loop? There is only one impedance Z Thevenin, and we have one source V Thevenin. So therefore the current that flows here, the short circuit current ISC, will be V Thevenin by Z Thevenin, and therefore I NOR is equal to V Thevenin by Z Thevenin. Thus we see that Norton equivalent and Thevenin equivalent are both one and the same, except that they are representing the circuit in slightly different forms. The parameters of the Norton equivalent I NOR and Z NOR can be related to the parameters of the Thevenin equivalent V Thevenin and Z Thevenin in this fashion as highlighted here.